knows, where I explain, say things about, and share facts about, as well as share my opinions about things that I happen to know about, which includes topics that cover basically every field. There's very few things I know nothing about. Now, for our first video, let's start with force and mass. What exactly is mass and force? It's very simple. Mass is the amount of stuff that something has, right? The more stuff it has, the more mass. And right now, I'm making this thing more massive. And force is the ability to take a mass and make it go and increase speed. That is force. That is the thing. That's mass and that's force right there, right? So we're taking this, it's moving at this speed. Now it's moving at this speed. We have just applied a force to this thing, right? Now, mass and force are combined in another unit, in another measurement, and that's called weight. In the common or person's language, mass and weight are often used interchangeably, but in this version, not at all. In this version, weight is simply mass times force, and force here is a force that's dependent on mass. Mass times acceleration is force. Mass times acceleration, right? Okay, but a mass, and then the acceleration, right? What exactly is the difference between mass and weight? Well, first of all, mass has an SI unit called, a simple unit called kilograms, and force is a simple unit called newtons. Acceleration has a simple unit called, of course, meters per second squared, or ms minus 2, if you really want to be technical, right? Now, to get a weight from a mass, what you need to do is you take the mass and you need to multiply by acceleration. By acceleration, right? So once you multiply a mass by an acceleration, you get something called a weight. And in SI units, in scientific terminology, the unit of weight is a Newton. Yes, Isaac Newton, the guy who was documented apples falling on his head, falling near his head, not on his head, but let's make it funny, right? It's named after him. And it's also said that Isaac Newton didn't actually discover gravity just from apples falling near his head. That was actually made up by someone called Voltaire, who was trying to explain to students about gravity. So he obviously was citing Newton. Obviously, it was Newton's theory. So he had to say that Newton saw apples. Now, that said, Newton did saw apples falling, but it wasn't like it was a bingo gravity exists. Like this was a more a more gradual thing with Newton. Okay. But yes, newtons are a unit of weight in SI. Weight is simply mass times acceleration. And here's another thing. Pounds, which are denoted by lbs, the short form of pounds is lbs. I can explain why in another video. Pounds are not a unit of mass. They're in fact a UK customer unit of weight. Right? So pounds are not a unit of mass, they're a unit of weight. Kilograms are not a unit of weight, they're a unit of mass. Nobody weighs 50 kilograms in science. Nobody weighs 60 kilograms in science either. No one weighs 120 kilograms in science either. You all have an estimated mass of 50, 60, and 120 kilograms, but the weight force, once you multiply by acceleration due to gravity, which is approximately equal to 9.81 meters per second squared, well, what exactly is weight called in science? Does anybody know? I'm going to give you a few seconds to find out. While I just clear up this whiteboard here. Weight in the United States customary system is noted in pounds. right? Weight in scientific language, in modern scientific language, is denoted in kilogram forces. Okay, I am not 53.5 kilograms, I am 53.5 kilogram forces, which would be about 118 pounds. So let me just put this out. KGF, right? KGF doesn't mean no. It means kilogram force. Right there. That's what KGF means. Okay? So once we have that settled down, mass is in kilograms. Weight is in newtons or pounds, or kgf, right? And weight is simply mass times acceleration, usually acceleration due to gravity, but in terms of g-force, it can be another type of acceleration as well. For example, when you're space launching into space in a rocket, it provides 4 g-forces because you immense upward acceleration, and there your weight is going to go from 50 kilograms to 200 kilograms right there. Right? So as we can see here, these are the two things. Kilograms, newtons, and meters per second squared. Now, what exactly is a force? A force is anything that can, well, momentum is mass times speed, right? And that would be force divided by mass into time. Force divided by mass into time is momentum. Momentum is directional inertia. The inertia of a body in a certain direction is its momentum. It's that simple. And that can be said as how difficult it is to remove the movement of a body. Very simple. How much force do you need to remove the movement of a body? That's its momentum, right? So once we have force, mass, time, this is momentum, right? And what do we remember? Do we remember the formula of momentum? I hope so, because M for momentum is determined by simple mass into speed, right? Inertia, therefore, is mass into direction, right? Momentum is mass into velocity. Momentum is determined by mass into velocity. And inertia is determined by mass into speed. Right? Mass into velocity and mass into speed. That is what determines momentum and inertia. Here's momentum and here is inertia. Right? So here's our mass into velocity and mass into speed, momentum and inertia. Now, once we have momentum or inertia, they both are under the same dimensions right here. What exactly is kinetic energy? Why exactly is mv momentum and half mv squared equals to ke? What exactly is kinetic energy? Well, what sort of mathematical equation, what sort of mathematical operation can you do to mv to get half mv squared? That you have to find out, right? It turns out that you simply have to integrate mv. And you have to integrate mv, mass is what? Mass is a constant. V is distance by time. You have to integrate mv with respect to time. And you're going to get half mv squared. And integration is simply advanced addition add up all the things under a curve line or whatever on the graph, and that's its integral right here. The integration of momentum with respect to time, anyone correct me if I'm wrong, is its kinetic energy. And now a practical way of putting it is momentum is how easily we can push something, kinetic energy is how easily we can push something. Right there. Sound itself is an energy, as you can see. So now that we have momentum and kinetic energy, the first integral of half mv squared with respect to v, or with respect to some part of v, with respect to v itself, half mv squared with respect to v, that's kinetic energy. But what else is also considered as equal to energy? Well, you're adding up work. You're adding up work with respect to, now remember, mv, momentum, the first integral of momentum with, it is integral, that's why the exponent has increased. Yeah, first integral of momentum with respect to displacement is kinetic energy. Yes. Now I finally remember. The first integral of momentum with respect to displacement is kinetic energy. These lectures are really helping me out. Now, that's the first thing, right? Then if kinetic energy is the first integral with respect to displacement, right? Kinetic energy is in kinetics. Things are moving. It's more easily affected by velocity, as you can see, than momentum is. Which is why light, you can push things with light, but you cannot push things very hard. But the same light, the same laser can burn your skin. That's an extreme example. And meanwhile, I can push this with my hand, but it's not going to burn anything. Another thing that's equal to energy is called work, right? So energy E, right, is equal to, it can be described as KE, there's one type of energy, and it can also be described as simply work. And work is what? Force times distance. Work can be against gravity, or it can be against friction, but it's simply force times distance. And another interesting fact to happen to know is that the size of a muscle is not determined by its force production capacity, nor its power, which is the next thing I'm going to speak about, is determined by its work capacity, right? So the more force that you can apply with a muscle for a greater distance, the bigger it gets. That you might want to remember. Work is Fd, and therefore Fd is equal to energy E, which is equal to half mv squared. Right there, Ft is equal to energy, which is equal to half mv squared. So that's the next thing, work. But here's another thing, power, right? Very often they say that an athlete might be strong, but they're not powerful, right? And when they're referring to that, they're referring to an athlete that can move a lot of weight, but they cannot throw a lot. They can't throw a heavy weight very far or very fast. For example, in powerlifting, someone might be lifting the barbell from here, and they're lifting it as slowly as they can, right? In Olympic weightlifting, they don't just lift it, they throw it. That requires a certain thing called power. Right? And what is the difference between strength and power? Let's see. Strength is the amount of force that someone can exert. It's that simple. It's not necessarily against gravity, but when it is against gravity, it's super easy to calculate and super simplified. So let's put up two more things. Force and power. force and power. What exactly is the difference between force and power? Also, how much time have I been live streaming by now? Only 16 minutes? Okay.
You have one viewer.
Force is the ability to take a mass and cause it to have acceleration, right? It's directly proportional to both mass and acceleration. It doesn't have any other proportionality constants. Power is force divided by time. MA divided by T, right? So as we see, between the person that deadlifted 100 kilograms like this, let's say they took 1, 2, 2.5 seconds to deadlift 100 kilograms to a height of 1 meter, versus the other athlete who snatched 100 kilograms like this. Let's say it took them 0.35 seconds to snatch, right? So the first athlete has a power, right? He was able to exert the same amount of mechanical work in less time. The 1 meter mark has already been passed. Let's say it took him 0.3 seconds. 0.3 seconds to snatch 100 kgs by 1 meter. And the other athlete took 2.5 seconds to deadlift. Same weight. Right? Both have exerted the same amount of force. Actually, the first athlete has exerted more force, but both have actually exerted a similar amount of force, right? Because most of the acceleration they're providing is simply negating the force of gravity. The speed of the snatch does do it, but then you can just add 40 or 50 kilograms to the deadlift, and now they both have exerted the same amount of force. But this athlete here, who snatched the weight, has exerted his force even with a lighter weight in less time. This is what they call power, right? Force divided by time is power. Okay? So here we do it. And when you exert this the greater force in less time, what else happens is that, well, the work you can do in that amount of time is reduced. Yeah, I told you already, the bigger muscle has a greater work capacity. If you develop power, then maybe your exercise sessions could be shorter and you still develop bigger muscles. Right there. It also takes more force to lift the same weight quickly as it does slowly, because you're going to have to provide a g-force acceleration, but when you're lifting weight slowly, you do not really need to produce much more acceleration than the acceleration due to gravity, but that's a topic for another video. So I hope everyone understood what force and power is. I'm going to edit this down into shorter videos. That's good for this live.
Who's the expert in the corner?